Hello friends, welcome back to the Dr. Tristos channel. I'm Dr. Tristos, your host. We're continuing along with our example demo, and in the last video you'll recall that we had tried to make it more readable and easily maintainable in the future, and it's doing that, trying to make it more maintainable, that the boss came in and he has another requirement. He said, you know what? He said, this prints hello world up here, but we probably want to change that in the future. And we probably want it to print more than one line and have additional messages. So you're thinking about it and you're thinking, oh, geez, that means I'll count the number of characters each time after a change and change the number of bytes here. And I have to count that. And you know, it's going to require a programmer probably to make these changes. We can't just let, a lot of people could go in and put the define byte and the double quotes and enter text. So a lot of people could do that. It doesn't necessarily take a qualified IT professional for that. However, the way the program is structured here, it is going to take a programmer to change it each time. So one of my first things is, well, the boss says there's going to be more than one line of text. That means I need to be able to go to a new line. And this is an ASCII chart, American Standard Code for Information Interchange, which is what the terminal programs are all going to understand. And if I look here, we have number 13, decimal 13, carriage return, CR. Well, carriage return is from the old days when we used teletypes and we had carriages, and I've done quite a bit of that. The only thing to note here is in Tristos, when we do a carriage return, it also does a line feed at the same time. A line feed is a decimal 10, and I believe with CPM and many other systems, if you do a carriage return, that simply moves the carriage to the left, or your cursor all the way to the left column. If you want to be on a new line, you have to then follow that with a new line, LF, line feed. However, in Tristos, the way the terminal is set up, anytime it does a carriage return, it automatically goes to a new line. So I only need this carriage return, decimal 13. So I don't want to remember that all the time. Let's go up here to our equates, where we had them before. And I'm going to say CR. And I'm going to put a .ASC, because this is ASCII, right? It's my own abbreviation, carriage return .ASCII, .ASC, representing ASCII. And here I'm going to put equate 13. Okay, there's no percent sign, there's no H, so the assembler is going to assume that that is a decimal number, and it is. Now, we can start putting in more text here, but we need another way of knowing. If we start outputting the text, we need a different way of knowing when we've reached the end of the text, rather than using a counter like we did here, because this requires us to count the number of bytes each time. It would also limit us that we couldn't output any more than 256 characters, because that's the longest this loop could be. So we need something better here. Let's just go ahead and put in what we want to define by this. Oops. Now remember, we said that we can have both character strings and bytes all in the same line. Here are the defined byte statement. We just need to separate them by commas. So let's put a comma here, carriage return dot ASC. Remember, we just put this in our equates up here. I got it right there. So now the assembler is going to assemble this text, this string of characters. When it comes to an end, it sees a comma, it says, oh, it's got something else for me. And this is not in quotes, so it's going to treat it equate 13. So it's simply going to replace inside the assembler. If you was to see this happen, it would assemble just like that. But here, for us humans, it's reading it. It's more readable if it's like this. So you know what? We need a carriage return on both lines. Now each line has a carriage return. And this is the only changes we needed right now, is this adding this one line. But how are we going to know we've reached the end? If we're outputting this string of bytes, how are we going to know that we reached the end? I guess we're going to have to put some kind of marker. Some kind of marker that maybe we don't ever, we only use when we want to indicate that we're at the end of a string of text that we're outputting. And let's look at our ASCII chart again. And, you know, I can give you a hint. Let's go down here to number 3. ETX, end of text. Now, these had a different meaning, especially in the days of the different types of protocols they had for computers communicating over phone lines in the 1960s and 50s, etc. Some of this has become obsolete, but we kept the names, and sometimes each manufacturer used these to indicate different things. As for example, in Windows, if you do a Control-C, you're doing a copy. On a lot of systems, if you're doing a Control-C, you're telling it you want to interrupt the system and get a some type of monitor or debug, or get the system to come to a ready prompt or something like that. But here for our text, since we're not actually printing this on the screen, we're just using as a marker ETX as a 3. So let's go back to our code, and let's go up here to the equates. We don't want to always have to remember this. Let's call this one ETX.ASCII. We'll equate that to a 3. Now, let's go back down and look at our program. We're loading the H&L register pair with a pointer that points to our data right here at the beginning. It'll point to the letter H, the first letter, when we do this load H&L. We're no longer counting the bytes this way, so we no longer need to worry about loading the B register. And you know, we still need to test the transmitter and see if it's empty and ready to receive a character. That remains the same. Now we get a character. So now is the time for us to compare that character. Is that end of text? Is this end of text block? So when we get to the last character, the end, you know, oh, let's go up here. We haven't done that yet, have we? So now we have our block of text that we want to output. We're going to define byte here. So now we have our ASCII text with carriage returns at the end of each sentence, which will skip to a new line. And when we get to the very end of our text, we have a ETX ASC, which is a 03 in ASCII. So we come down here and we're outputting, and we get a character here. the character that's being pointed to by the H&L register pair, and we compare that. Is this the end of the text block? Is that the end? Okay, so now we're going to, if that is true, it's 0. Well, we don't know exactly where we're going to go yet because we don't have a label down there at the bottom. So we're just going to have to make a mental note that we created a label here. No more text. Okay. If it was non-zero, we're going to continue here and output the byte. Then increment the H&L register pair to the next we're going to increment the H&L register pair to point to the next byte in the text in the text we're working with. Well, now we don't need this decrement and jump non-zero. Actually, we just need to go back around again. We've already determined here. We tested to see if this was the end of the text. No, it's not. No more text. We determined we have more text, so we output that. We point to the next one. Then we naturally just go back around again, test and see if it's ready. When it becomes ready, we get the next byte. And let's say this is, we've already output all the text, and we receive a compare end of text, and this time it's 0. It's true that this is the end of text. No more text. So we don't want to output. We don't want to increment anymore. We don't want to jump around. We simply want to go here to our halt statement. Okay. So as soon as there's no more text, we'll bypass the code directly below that and go directly to the halt statement. We can take this comment out because we're not testing B any longer. We're still bumping the pointer just like we did. It's out the IO port. All of that remains the same. What we've added is getting the character, testing if this is the end. And if it is, we're going to go to the end of the program. So now, pray for me here, guys. Hopefully this will assemble with no syntax errors. It's not very often I write things and it assembles with no warnings on the first time. So it looks like we got no warnings, no errors. That compiled great. Let's run it. We're going to hit download and go. Again, downloading this to the simulator. And now if we look on the right, on our UART0, we have the hello world. And just for fun, we'll look at UART1. There's nothing there because we've never output anything to UART1. We're only dealing with UART0 in this example so far. So now we have hello world, and there's an example of our code. If someone comes in and says, well, we want to thank everybody for watching this example, or thank them for trying this example, it's easy for me to go over here as long as I put the text in correctly. Define byte, couple of tabs there. We use the tabs and not spaces. Thank you for trying this demo. And put a carriage return at the end of that. And you know what? My boss came in and he said, we can make that look a little neater. Let's put a blank line between a couple of the lines. So look, if we have a carriage return there, now let's try this. Let's make sure that it assembles with no errors, that I didn't make any typographical errors. No, I did not. We're going to download and go, download it to the simulator and go. So now if we look, we've added another sentence and we have a blank line between it and the sentence that was already there. So here's an example of using these control codes of carriage return, end of text. Now the terminal itself, or Zilog development system, it doesn't know anything about this end of text ASCII code. You and I are doing that right here in the code that we write. We're the ones that's defining what this end of text does when it runs across a number 3 and outputting. We're defining that here in the program. It's not something that's done by the assembler itself or the development system. Okay, so we could have easily made this a different code. If we looked over in our ASCII chart and we said, I don't know what device control code 1, it's number 17 in decimal. I don't know what that is, but that's what I want to use to indicate the end of my text block. You could do that if you want. It's not going to know the difference. Now, I will tell you, if you're outputting to a terminal and you were to send some of these different codes, that could have an unwanted result. But here, if you notice the way we've wrote this code, we never actually send the 03, the control C, the ETX. We never actually send that. As soon as we compare it and see that's what the character is, and we confirm that that's true, we immediately drop through to no more text. So here we've learned a way to write this. You talk about maintainability, portability. Well, doesn't really necessarily make it portable, but it's maintainability and the readability of the program we're writing. Here it's becoming a lot clearer. And a lot easier to maintain. We no longer have to count how long our sentences are and add up all the bytes and load a counter, and then, what if one day the boss comes in and gives me more than 256 characters to output? I would have to break it into multiple chunks, and here we've solved that. Theoretically, I guess you could output 65,536 before it would start repeating bytes with this program. But that's not going to happen. There's a lot of reasons why that theoretically would not happen. But theoretically, you could keep incrementing the H&L until it reached FF, and then one more, it would roll back over to 00 and keep scrolling through memory. There's a lot of reasons that probably wouldn't happen. It's going to run across patches of data, and it'd probably see a 3 in memory, and that would cause it to stop. Or there could be other reasons that would cause it to stop before it would. But let's do that. Let's take the end of text out and just see what it does. I suspect we're going to get a long string of characters, but it will eventually stop. So I'm gonna put download and go, which it wants to know if I want to rebuild. It can be done in one step there. And so if we look, we got an exclamation point. If we were to look in RAM, at some point it got an exclamation point. It was in RAM. It output that. At some point it ran across a 03. If we look at our assembly, so we can kind of figure that out. If this is our text up here, and we go to the listing, the assembler output, here's our assembler output. And here is the beginning of our text, our data stream right here. And here is this data in ASCII. And if we come down here, we see that we made the ETX a comment line. So it assembled nothing. But still, if it actually became pretty easy here. The first instruction, after all the data, we begin a no-op. There's your 00, the no-op instruction. Then begin app, the next instruction, load H&L with data. Well, 21 is the opcode for load H&L with an absolute value. 21 is the opcode. The address is 03 3003. This is stored little ending, big ending format. So the little ending is first, the big ending comes last. The address is 3003. So the little ending is 03. And guess what? Magically, our program only output is 00. If we look on an ASCII chart, 00 is a null, which means nothing's going to happen. Okay. Then if we look, the next one is a 21. That's in hexadecimal. Let's look at a 21 hex. And if we look, it's an exclamation point. 21 hex is exclamation. And that's exactly what we're getting in our demo program. An exclamation right there. Then it pulls that 03 the next time, and it stopped the output. So that worked out pretty nice for a demo. I got to tell you, I didn't plan it that way, but it works out pretty nice. That just a couple of bytes down was an opcode that used an address, and the little ending of that address was 03. So I hope maybe this explains some more things. I'm hoping that you can't really use this as an assembly language tutorial. I'm trying to get people's feet wet with the Zilog development system. However, probably you already know something about assembler, have used other assemblers, etc. There's a lot of things that the Zilog development system does not do that our old Z80 tools did, providing symbol tables and cross-reference tables and just a lot of things I miss from the original. But this also, the Zilog development system, does some new powerful features that we couldn't do with the old tools. So again, if there's anything I can help you with, please let me know. Again, many thanks for watching, and I hope to see you here again on the Dr. Tristos channel.